Anybody know how snowboards work? Or half pipes work? All right, so when you have a half pipe, and what's interesting is we went skiing last year, and I saw my first half pipe, like Olympic half pipe, in person. Wasn't person. I was, so that counts. And it's crazy how steep it was. It wasn't ready for how steep, but that's how they get their speed up for sure. So I'm going to show you a video of Chloe Kim's Olympic gold half pipe run. It won't be on the video because the last time I included it on the video, YouTube snagged me for copyright, and then the whole video didn't get posted. So that was a bummer. So I'll post the link if whoever is listening to this video that's not here today that wants to watch the video, if you want to watch it again, the link will be posted, but I can't show the video on this video, or else I can't post the video. You're with me on that, right? All right, so what we're going to do is we're going to sketch her height over time on the graph below, and I want to make sure that you understand that the height is measured above the lip of the wall. So the snowboarder comes down, and throughout there's this platform deck where she starts on, and then she comes down. This is going to be our 0. And then we'll go through the time and we'll record her heights, and what happens is the run shows the heights, and we're going to go ahead and add 7 meters to that when we talk about our heights, because they talk about the height above the lip, but we want her height from 0. Everybody okay with that conversation? All right, so when we look at this graph, this is a position graph, her position over time. So when we talk about different layers of our function, whether we're talking about position, velocity, or acceleration, we're talking about her position. And today we're going to be bringing back IVT, our intermediate value theorem, and we're going to add to the mean value theorem. And the mean value theorem is the same kind of conversation about, can you guarantee a rate of change in between two other rates of change? IVT asks us, can we guarantee a position in between any two positions? If you go back to that delta math that we had, they had you, let's fill in this box with, I don't know, we'll do blue for snow. Is it filling? Why didn't it fill? We'll try this again. If you remember IVT had us looking at kind of like this mystery box. I'm trying to find a good place. We'll start here. Okay. If I know that this here point is guaranteed, and I know this is guaranteed, IVT guarantees that everything in between those spaces is guaranteed. So today we're going to learn about our mean value theorem, and our mean value theorem talks about a similar idea, but in idea of rates of changes. But it's important to look about this idea of an average. So my green dotted line across here is what her average height was during her trip. So here's where she's on the lip, about to start. She starts going down, and she's up, down, and in each of these positions, if you think about her velocity, where she's gaining speed, losing speed, where velocity and acceleration are working together and against each other, it's kind of a crazy graph to see her position going up and down. What's interesting is we know that her height, her average height, is where this green dotted line is. And an important thing to remember about this idea of average is the same amount of data points are above it as below it. But at any given point, I know that she had to at least be going that average, have that average height at any given point. That is a value that's on my range of outputs. Because I have values above it, I have the values below it, but I'm guaranteed to at least hit it. Does that make sense to you? All right. When we're looking at our data, we know that she had this one maximum height, but then she had this average height. And then, is there a time on the interval where her height is guaranteed to be the same as the average? Yes, it is guaranteed. And we want to think about this. similar to IVT where that value is guaranteed on that interval, but also a conversation that we're going to take that same idea and talk about rates. Flip your paper over. Anybody ever drive on the turnpike in Pennsylvania? Watch out. Pennsylvania is nuts about speeding and giving tickets. So now, especially that they have these electronic speeds, what they can do is they can look at where you got on to the turnpike and where you got off, and they can calculate your average rate. And if electronically they look at the time it took you to get from one toll base to the other, if it's on average faster than their speed limit, you get a ticket. Electronically, they take a picture of your license plate and they send it to you. You've been warned. But they can figure out these conversations. So I want you to think about this. If I'm traveling on a 70-mile stretch of turnpike and I cover those 70 miles in 1 hour, what does that mean?
Your average speed is 70 miles an hour.
Okay, so when I'm looking at, and we know that our distance is equal to my rate times time, right? And if I covered 70 miles and I have 1 hour, then I know that on average I covered 70 miles in 60 minutes. So my average speed was 70 miles per hour. Now here's the thing. The old style toll booths had human beings in them that you actually had to stop and pay a toll. The new style toll gates, especially if they have these things, make you slow down to go through. But there's no way that my slowing down here and my speeding up here had me averaging 70 miles per hour without me going faster, because I had spent that time going slower when I was speeding up or slowing down. Are you okay with that philosophy? So when my speed went slowing down, speeding up, slowing down, if my average speed across this whole time was 70 miles per hour as an average, you have to understand that there are times when I was going faster than that, and there were times that I was going slower than that. Does that make sense to you? So that's going to be the crux of our mean value theorem today. We're going to learn that at any given point, any instantaneous rate of change is going to be the same as that speed, recognizing that there are times I'm going faster and times I'm going slower. When it comes to dealing with IVT and MVT, and we're going to talk about the extreme value theorem at the end of today, they find ways to take lots of points off of you for very non-calculus things, and it all has to do with take your brain mentally back to when you were in geometry, and if you didn't say the proof and the right theorem and the right converse, or you didn't do things in the right order, you lost points for it. So in the same concept, there's two kinds of things happening on your AP Calculus exam. Number one, some super tricky math that you want to make sure that you do, but also some super picky way of answering. So you got to balance the tricky and the picky. And the picky things are, before you can use IVT or MVT, you have to make sure that the criteria of the theorems are met. So when you're talking about IVT, you cannot use the intermediate value theorem unless you know your function's continuous. We're going to talk about the mean value theorem today. You can't use that unless you know your function's differentiable. You have to state, and the way this output inequality is stated, it has this kind of reverse thing going on, because you're stating your lower bound and your upper bound. These are your lower and upper bound inputs. These are your lower and upper bound outputs, and you're trying to prove if an output of, for example, 5 is necessary. So you're going to have to state that inequality that there is that range for it to exist. The sentence that they want you to state after you have these two qualifications met, therefore there's going to be a value, because what you're talking about is an input of C on that range. So you would say, yes, there must be a value of C in between. And for this example, here is our 0 and here is our 8, such that this S of T, and that's your output. This will make more sense after we have our lesson today, but go ahead and keep this paper handy, because if you get in good habits of stating your answers in a way that makes good sense, then you're not losing the picky points. If you're gonna lose points on the AP exam, lose the tricky ones, not the picky ones. You know what I'm saying? All right, what I'd like you to do right now. All right, so when we're using the mean value theorem, in this instance, when we're talking about that mean is where we're talking about that average, and we're going to be talking about rates in this, whether we're talking about your average rate of change and your instantaneous rate of change. One of the qualifications is we need to make sure that your function is continuous over a closed interval. And this is intentional, where we want to make sure you know that it is the closed interval. So if it's continuous over that closed interval and then differentiable over the open interval, then there's going to exist some point C within that open interval where the instantaneous rate of change equals the average rate of change over the interval. And to me, that paragraph seems a little bit of a word salad, so it helps me if we go ahead and draw a pretty good picture. Give yourself a cubic function with distinctive humps. And then go ahead and give yourself an A value and a B value. Let me redo that. An A value and a B value here, and we can talk about their output values here. So we know here is my output value with A as an input, and then here we have my output value with B as an input. If I were to calculate my average rate of change, I would be using the slope of the secant line as that calculation. That is my average rate of change over that interval. That's why the interval needs to be closed, because I need A and B as input-output values. So that validates why that interval is closed. Everybody okay with that conversation? All right. What they're saying here is there is going to be a time C on this interval, and it doesn't matter whether we're talking about C being anywhere along here. There's going to be a time where C is on the interval of A and B, where the instantaneous rate of change is the same as the average rate of change. And what we can do is we can go ahead and look at that and see this instantaneous rate of change, if I'm eyeballing it, is going to be parallel or have that same slope value in our drawing here of two places. So we can say that there's going to be somewhere on this interval where this C, and if it happens once or twice, That's a possibility, but there's going to be a place somewhere on that interval where my instantaneous rate of change is going to be the same as my average rate of change. Just like when we talked about Chloe Kim, there was a time when her height was the same as that average height. Sometimes it was higher than it, sometimes it was lower than it, but there was a time along her trip where she was the same as her average height, no matter what. When we go ahead and we calculate this, what we're saying is that this instantaneous rate of change at some point is going to be equal to our slope conversation, which is our average rate of change. So to me, it feels like one of those very logical conversations where you're like, well, of course it is. But we want to make sure that we understand why that's true. All right. So we'll go ahead and look at this first one. If we use this function to answer the following, on that interval, what is the average rate of change? If we're taking the part of the test where we have no calculator, then it's up to us to do these calculations. If we're taking a test that has the calculator or Desmos, we want to be timely. So I want to talk about some tips and tricks ahead of time so that if you are in the calculator section, you know what to do. So take a minute, get your calculator out. If you need to borrow one from me, please do so. Us to find instantaneous rate of change and average rate of change on an interval. What's super important is that you're intentional about knowing what the output with an input of each of these values is. When we're given a function, sometimes if we have a calculator, it's faster to enter the function into the graphing calculator and use the table of values for input-output values. I know you can add, subtract, multiply, and divide, but I've got a whole wall of Smarties up there for every time I screw that up. So the very last thing that I want is to be messing up on my calculations when I'm going to be using them in the future. So if it's a part of the exam that lets you use the calculator, don't be a hero, use the calculator. All right, so we'll go ahead, go to the table of values. Everybody know where to enter this into the calculator in the function screen, yes? So when we go to the table of values, it's as easy as looking at these input-output values. So we're talking about f of 2 is 12 and f of 6 is negative 8. If we're taking a test and somebody is grading our work, that's enough to say that you did that math. So they want to know what the average rate of change on that interval is. So your average rate of change is going to be equal to, and make sure you get in the habit of doing your second output. So whether you're talking about whatever's coming in your story first or second, especially with the related rates where we want to know, is something shrinking or am I moving left or right? Get in the habit of making sure you're doing f of b, your second point, first. So then we can just go ahead and say here, negative 8 minus 12 over 6 minus 2, which is going to give us that negative 20 over 4, which is going to give us negative 5. And do they give us any units?
No.
Average rate of change. So if they don't give us any units, then that's the best that we can do. All right, so the next question is like, okay, on that same interval, when does the instantaneous rate of change equal the average rate of change? So here is where you're having a conversation about your instantaneous rate of change, which you need to know goes back to your derivative, which goes back to your slope of your tangent line. So now your mad derivative skills come into play, where you can go ahead and you can do that. There's nothing wrong with you going and entering this second equation, negative 2x plus 3, in this category, or in your y2, and then going to your table and you're looking at, do I have an output of -5? Because that's what you're solving for. So if you have the opportunity to use a calculator, you want to make sure that you know that sometimes graphing the original equation and your derivative equation at the same time allows you to find some pretty quick input-output table or input-output values just by using your table of values. If you don't have a calculator, then the work that you're doing is taking this -5 and saying, okay, when is this what's happening? And then doing your basic algebra to solve. And you have that when x is equal to 4 is when you have that instantaneous rate of change equal to that value. When we look at MVT and IVT together, we want to make sure that we understand that one is about position and one is about rate. So when we're talking about IVT, that's on that given interval, you're going to have a Y value. Think about this Y value as your output in terms of position. You're going to have a Y value at each of the endpoints of the interval, and every Y exists between these two. And you want to make sure the number one thing that you consider is first, if the function is continuous. So that's what we've already done. Today's conversation, when we're talking about the mean value theorem, we're saying that there is a derivative, an instantaneous rate of change, that's going to be equal to the average rate of change somewhere in that interval. And we want to make sure that my average rate of change, we know as my average rate of change, that is my slope of my secant line on that closed interval. And we need to make sure that this conversation is differentiable. If it's not differentiable, no mean value theorem. So think about that difference between something being continuous and differentiable. If it's continuous, that's where we talk about the limit from the left and the limit from the right matches the value, no holes, no jumps, no asymptotes. That's continuity. When we're talking about differentiability, we just need to make sure we have no cusp sharp points. So things like absolute value functions are not going to be differentiable unless they give us an interval that doesn't include the point. All right, we'll see how this works. So when we go ahead and we turn the page, a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height measured in feet at time t measured in minutes. The table above gives the values of the height of the balloon at selected times t. Okay, so for a time interval between 5 and 15, must there be a time when the balloon is 50 feet in the air? And when we say justify your answer, that's the picky part. So do me a favor, turn to your partner, look at the chart, decide yes or no, and see if you can get the sentence validating it correct from the bottom of the warm-up. Turn to your partner and say, let's go. The answer is yes, because when we look at the chart, we know that the hot air balloon at 5 minutes is at 40 feet in the air, and at 15 minutes it's at 70 feet in the air. So was there a time in between there that it hit 50? Yes. So that's not gonna get you points. So yes, because if you go duh, that's not gonna get you points. So what will get you points is, once they say it's twice differentiable, you gotta say it's continuous. If you're talking about IVT, it's about continuity. Did you get that? Then you have to say that on these, as part of your two boundaries, an input of 5 has an output of 40, which is less than 50, which is less than, and notice how they spun this equation around, 70, which is the output with an input of 15. So this sentence here talks about output in your answer. Therefore, by IVT, there must be a value t in between 5 and 15 so that this is true. These are the requirements before you can use the theorem. You don't have to state them in your fancy answer, but you do have to state them. Because H is continuous and this output is between those outputs. Those things you can state. Because those two things are true, therefore you can apply this theorem because it meets your qualifications. These are your qualifications. Here is your ribbon on the top of the present. Therefore, by IVT, there must be a value between 5 and 15 such that that height is right. Does that make sense to you? On a scale of 1 to 10 for picky, do you put that up at like a 9 or a 10? Because I do too. But it's not tricky. So we want to make sure that if we're going to lose points on the test, we lose the tricky ones. Are we okay with that? All right, let's look at a time between 20 and 30. Must there be a time when the balloon's velocity is 1.5 feet per minute? So the answer here is it don't have velocity. It don't have this here. But can I figure out my average rate of change, my slope of the secant line between that closed interval? So they're talking about 20 to 30 in this one. So this is going to be the interval that I'm talking about. So we're going to go ahead and say that H of 20 is equal to what, and H of 30 is equal to what. So get those two values from your chart. H of 20 is 65, and H of 30 is 80. Is that okay? All right, so when I want to find that average rate of change, I'm going to go ahead and figure out my 80 minus 65 over 30 minus 20. And I'm going to say that that average rate of change is, what's that, 15 over 10? 1.5, what are our units? Feet per minute? So that's going to be our average rate of change. But what we want to do is make sure that we state the data so that we end up with what we need. What do we need to say about my function? That is differentiable. How's that different from continuous? Yeah, it has no cost, but I'm talking about rates. So when I'm talking about position, that's just, is where my output values are. But if I'm talking about rates, aren't I talking about derivatives? So I have to make sure I can take the derivative. That's why continuity matters for position, but differentiability matters for rates. So the first thing that we're going to make sure that we state is that H of t is differentiable. So when we apply the mean value theorem, we're going to go ahead and say that as long as our time is in between here, I'm guaranteed to have that because I've met the qualifications of what has to be true. Because it's differentiable. So then we can say, therefore, by our mean value theorem, there must, not mush, must be a value, and I'm going to make sure is, because it's asking me, must there be a time? There must be a time of t in between 20 and 30 such that, and then we're looking at our velocity, so we're going to include that the velocity is equal to 1.5 feet per minute. For 20 to 30, must there be a time when the balloon's velocity is 1.5 feet per minute? Yes, there is, because of the mean value theorem. Here's my average rate of change. This is differentiable. As long as my t is in between my input values, my output's guaranteed to be between that average rate of change. You okay? Alright. So there's some practice that I want you to do, and I'm gonna give you, we have a little bit of extra time today because we didn't have homework or anything to go through. So I'm gonna give you a couple minutes to get started on the practice, and I want you talking to your partners, and I want you holding each other accountable using the template that's at the bottom. If this way of writing it out doesn't make sense to you, write it out in a way that does. What is your input? What is your output? What are the qualifications of each of the theorems so that we don't use the picky points? And then we're going to come back in and talk about our next idea. So I'm going to give you about 15 minutes. Turn to your partner and say, let's go. All right, so Skater Sully is riding a skateboard back and forth in the street that runs north-south. The twice differentiable, got it. Function S models his position on the street, measured by how many meters north he is from his starting time, seconds from the start of his ride. The table below gives the obvious, so here's the time and here's his position. Position, they can ask us about IVT, or we're going to be finding average rates of change to support MVT. So they want to know between 0 and 20, must there be a time when he is 2 meters south of his starting point? So that's asking me about an output of -2, right? 2 meters south. You okay with that? So yes, and make sure you say the following. Yes, the function's continuous. My output at time 0 is 0. My output at an input of 20 is -5. So by EVT or by IVT, there's an output, there's a value C such that my output is equal to -2 and C is in between 0 and 20. Here's an input conversation here because, and that value -2 is guaranteed between 0 and -5. That's an IVT conversation. Okay, for B, between 30 and 60, is there a time when his velocity is 1.1 meters per second? Yeah, because guess what? It's differentiable. Did you get that down? And my average rate of change is 1.1 meters per second. So yes, according to MVT, there must be a value C in between 30 and 60 where his instantaneous rate of change. How'd you do with your picky? Pretty good? Okay. Good habits start now. Did you do number 2? A particle is moving along the x-axis. The twice differential function S models the particle's distance from the origin measured in centimeters. At a time t in seconds. Okay, so between 20 and 25, must there be a time where the particle is at the origin? Right? Yes. It's continuous. My output at 20 is 10, and my output at 25 is 8. I prefer using the inequality on this output conversation. So if you look at what I prefer to guarantee getting all my dots covered, because S of 20 is equal to negative 10, and that's less than 0, which is my origin, which is less than 8, which is equal to my S of 25. I like this better, because to me, this part here doesn't quite guarantee. I know origin is at 0, and I know it crosses the origin, but I don't want somebody being so picky that I don't get points for that. If they say, must there be a time, I also prefer the word yes in front of this. Yes, there has to be a time. According to IVT, there's a value C such that my output is equal to 0, because as long as C is in between these two lower and upper boundary markers. All right, so for any time between 3 and 10, must there be a time when the particle's velocity is negative 1 centimeters per second? And I'm getting the feeling like so much of these are contrived. Like, what a coincidence. It works out to be my average rate of change each time. So yes, because the function is differentiable, I can figure out my average rate of change is equal to negative 1. And I would again add units onto this. I'm not losing picky points. My average rate of change is negative 1 centimeters per second. So yes, according to the mean value theorem, there must be a value C in between 3 and 10, where my instantaneous rate of change is equal to negative 1 centimeters per second. I would definitely add that on. Did you do the hot air balloon one? Did you go on and keep going?
Yeah.
For those of you who did your hot air balloon is launched into the air with a human pilot. I wonder why that matters. The twice differentiable function models the balloon's height measured in feet at time measured in minutes, blah, blah, blah. Must there be a time when the balloon is 50 feet in the air between 6 and 10? No. Can there be? Yes. Must there be? No. See the difference? Maybe the balloon went up and down, but I can't guarantee it, because think about, again, if the balloon is here, here's that box we don't see, and here's this. The balloon could have done this. We don't know, right? But the only thing that's guaranteed is these values here between those. So the green is possible, the purple is guaranteed. So no. IVT does not guarantee a height of 50. Between 10 and 40, must there be a time where the balloon's velocity is 3 feet per second? Differentiable, average rate of change is 3, so yes, that's guaranteed. All right, so the rest of the practice is just having you find where the instantaneous rate of change, and again, what great derivative practice, because your steps here are going to be to find the average rate of change, and then take the derivative, set that derivative equal to that average rate of change, and figure out those x's where it happens. Don't forget this trig conversation when you're talking about whatever intervals you're on, so pay attention to those. Yes?
For A on number 3, when we have to put like the function of s like at 6 is equal to 46, do we do it in inequality, or do we still put it like how the answer key put it?
Well, you're saying no, so your answer is a height of 50 is not guaranteed. I think an inequality justify, like, it would be a better answer if you say, because,
46 is less than 50, like 46.
right, because 50 is not in between 46 and 35. I might actually take the time to write that out instead of saying my not inequalities. You know, this is this and this is this, so IVT doesn't guarantee a height of 50. And I would add another sentence here because 50 is not between 46 and 35 feet. That's what I would do, just to make sure that there's no doubt. Did I answer your question, Madison? Are we good? All right, so in the last couple minutes, this first couple lessons of this one is a little tricky because we wanted to fit 3 lessons into 2 days. So we kind of just go ahead and talk about critical points. I think you've had a lot of this before. We're just putting it now into calculus terms. So if this is going too fast for you, we'll go back and we'll revisit it again next class. Our next conversation is our extreme value theorem. And our extreme value theorem says if a function is continuous over an interval, then it has at least one min and one max. So if you think about it, if you play over here, there's no way that you can draw any kind of function that you have that doesn't have at least a minimum and a maximum. Like, don't draw a circle because that's not a function. But whatever function you draw, there's never going to be a time that it doesn't have at least one maximum value point and one minimum value point. So we got to spend some time talking about what mins and maxes are. And you learned them in an Algebra 2 pre-calc conversation, but now we're going to talk about them, and we're getting ready to talk about them from a calculus view. Depending on what textbook, website, resource that you're using, whether you call them global or local or absolute or relative, these are synonyms. So when we're talking about a global or an absolute min or max, we're talking about the highest or the lowest. When we're talking about a local or a relative min and max, we're just talking about an area on the graph where everything else is either lower than it or higher than it. So in Algebra 2 and pre-calc, you talked about your hills and your valleys. So think back to those terms. Anytime we're talking about the word extrema, we're talking about mins or maxes. That's just a fancy word that talks about them both, extrema. All right, so when we look at this silly function here, we've just got everything going on. We've got holes, we've got jumps, we've got it's definitely a function. It passes a vertical line test, but we've got values high, high, and low, low on both of it. Put your finger on what you think is the absolute max of the graph. Okay. Is your finger here? This is going to be our absolute maximum because it is the highest output value on our y-axis. Put your finger on what you think is the absolute minimum on the graph. So we're talking about here is going to be our absolute minimum. So our absolute max is the highest point on the graph, absolute min is the lowest point on the graph. We've got a lot of other stuff going on for sure. And that's when we get into talking about our relative or our local mins and maxes. And I gotta tell you something, I'm guilty of using the absolute and the local. So I mix up my groupings, so sorry if that's confusing for you. When you were in Algebra 2 or pre-calculus, you defined something here as a local minimum. And when we used to talk about that local minimum, we said that both points on either side of it were higher than it. And it's not really a formal definition, that's what's coming next with the calculus. But if you look on either side of this point, both of the output values on either side of it are higher than it. That's what makes that a local minimum. We can also call this one a local minimum, because when we're looking at this point here as a local min, are both points on either side of it higher than it? Yes. My question for you is, would you call this a local maximum? By definition, if it is, both points on either side of it are lower than it. Is that the truth? So this one is not going to be a local maximum. If it were here, we could say yes, but because it's underneath the function, it's not going to count. Would you call it a local minimum? Are both points on either side of it higher than it? In the mathematics community, there's lots of argument over this guy because not everybody agrees with what to do with him. He is not an absolute anything. We had our absolute minimum here, we had our absolute maximum here. And whether or not he is a local max is up for debate. Some teachers will say yes, he is a local max, because there's this point here that is lower than it and nothing after. Some teachers will hold true to the point that he is not a local max because there's nothing to the other side of it. The one thing that's guaranteed is no one on the AP exam is going to ask you about that, because nobody in the mathematics community agrees about it. So we're going to leave that one sit. All right, would you please take a look at these graphs and talk with your group about where you think you see local and global, or absolute and relative mins and maxes. Talk about 1 and 2. Go. All right. So when we look at this, again, picky versus tricky, we want to make sure that we express things the way that they want us to say. So when we're asked to find all extreme values, we want to make sure that when they talk about all extrema, they want both our local and our global. Is that the word? Both our absolute and our relative. So they want us to talk about all these points on the graph where stuff is happening. Think of it as the highlight reel. So if I'm going to talk about this graph, I'm going to say that there is an absolute minimum of 1 at x is equal to -3. So I'm doing two things there. I'm saying what the value is, and I'm saying where it happens. And both of those things have to be included. Picky, not tricky. You with me on that? When I'm talking about my maximum, I'm going to say that there is an absolute maximum of 5 at x is equal to 0. So I have my minimum and this max. So Sammy asked me, if it's an absolute, do you have to also talk about it as being a local? No, it's either one or the other. So here, if I'm going to start talking about a local minimum, when I look here at this point here, your question is, are there points on either side of it that are higher than it? So if I'm sitting here at this point here, can I look up and see the function? So if a little ant is sitting here and he looks up, does he see a function, a value that's higher than it? Yes, he does. Does he see a value of it that's higher? Yes, he does. So there's a local min of 2 at x is equal to 1. And that's it. We're not going to have an argument over this point because there's no value there. Make sense? We'll talk more as we get into next class, but I want you to look at these graphs and go ahead through and see if you can identify. Can I have 2 minutes, don't I? What I want you to be able to do is I want you to look at every single point. See, the board's arguing with me too. The board's like, I'm done. When we look at every single point that's part of our conversation of, is it a min or is it a max, I want you to think about, from a calculus view, what is happening to our derivative at each of those points. And that's where we'll stop.